So welcome to today's deep dive. Our mission today is to unpack a massive stack of corporate and technical source material we've got straight from Boeing.
Yeah, specifically detailing their brand new 777X commercial aircraft family.
Right. And, for decades, I think the one thing you and I, and really anyone flying just took for granted is that commercial airplanes are rigid.
Oh, absolutely.
Like from the moment they leave the factory to the moment they touch down, they are these static, unbending metal tubes. But that fundamental rule of aerospace architecture is, well, it's literally bending.
It has to be. I mean, we are hitting the absolute physical limits of what our current global airport infrastructure can handle.
Yeah.
But at the same time, airlines are demanding just unprecedented levels of efficiency from these machines.
And that tension, that exact tension between aerodynamics and physical concrete is what we're getting into today. Because imagine looking out your terminal window and you're watching a 235-foot metal wing physically fold itself in half.
Just to squeeze up to the gate.
It's to fit. It's wild. So today, we're looking past all the corporate jarring, past the whole flight experience of the future marketing gloss, to see what this machine actually is.
Right, the actual physics and the economics behind it.
Exactly.
Yeah.
Because we want to know what it looks like, what it sounds like, and what it costs.
Because when you start messing with the fundamental shape of a commercial jet, you aren't just making a slightly better plane, you're triggering this massive cascade of changes.
Like what?
Well, everything from the decibel levels in the neighborhoods around the airport to the literal multi-billion-dollar balance sheets of global airlines.
Okay, so let's start with the most jarring visual, which is the sheer anatomy of this giant. The size and, of course, that folding wing.
Yeah, it's impossible to ignore.
I'm looking at the specs for the 777-9 model right now, and the numbers are they're hard to even wrap your head around. The fuselage itself is 76.7 meters long.
Which is over 251 feet.
Right. It's just massive.
Now, it is a flying leviathan, honestly. You are talking about one of the longest commercial aircraft ever put into production. But the crazy thing is, the length isn't actually the engineering bottleneck here.
Wait, it's not?
No, the bottleneck is the wingspan.
Ah, right. Because once this plane is up in the air, the wingspan extends to 71.8 meters.
Which is about 235 feet across.
And it's powered by these absolute behemoths, the GE9X engines by GE Aerospace. But then when it lands, those wingtips mechanically fold upward, right?
Yeah, they hinge up, and that shrinks the total span on the ground down to 64.9 meters.
So just under 213 feet.
Exactly.
So, okay, looking at this, my immediate question, and I'm sure anyone listening is thinking the same thing, is about the risk.
The moving parts.
Yeah, like why go through the immense engineering headache of designing a wing that folds on a hinge? I mean, putting a moving joint on the single most critical load-bearing structure of an airplane sounds terrifying.
It sounds like a massive complication.
Right. Why not just build a plane with, slightly shorter wings from the get-go?
Well, because if you did that, you would be leaving massive aerodynamic efficiency on the table. So in aviation, the holy grail of wing design is something called a high aspect ratio.
High aspect ratio. Meaning what, exactly?
It means a wing that is very, very long and very thin. You see, when a wing generates lift, the high-pressure air under the wing tries to escape to the low-pressure area above the wing.
Okay, that makes sense.
And the easiest way for it to do that is by spilling over the wingtips. But when it does that, it creates this spiraling vortex of air that literally drags the plane backward.
Oh, wow. So it's called induced drag, right?
Exactly, induced drag.
So those are they're basically invisible tornadoes trailing behind the wingtips, forcing the engines to work harder.
That is a perfect way to visualize it. So by extending the wingspan to 71.8 meters, you move those vortices much further away from the fuselage.
You're minimizing their impact.
Precisely. A longer, thinner wing just slices through the air with significantly less drag. And less drag translates directly into lower fuel consumption.
So if you're an airline flying, say, New York to Dubai, you want the longest wing that physics will possibly allow.
You do, but then the reality of concrete and asphalt steps in.
Right, the airports.
Yeah. The global network of airports categorizes their gates and taxiways by size, and a permanent 71.8-meter wingspan bumps this aircraft into the absolute largest size category.
Which is code F, according to the source material.
Right, code F. And most major international hubs, places built decades ago, they simply do not have enough code F gates to accommodate whole fleets of these planes.
So if airlines bought a rigid 235-foot plane, airports from Heathrow to JFK would have to literally tear up concrete.
They'd have to widen taxiways, space out their gates. I mean, you're looking at a multi-billion-dollar global infrastructure overhaul.
Off to park the plane.
Exactly. So the folding wingtip is essentially this brilliant mechanical compromise.
Because shrinking it down to 64.9 meters folded allows it to squeeze into standard code E gates.
Right. It gives airlines the aerodynamic dream up in the sky without causing an infrastructural nightmare on the ground.
Okay, but back to the safety thing. A folding wing snapping mid-flight is nightmare fuel.
Oh, absolutely. But to convince regulators it's safe, they basically have to treat that hinge like a bank vault. They use these massive, redundant titanium locking pins.
Wow. Titanium pins.
Yeah, and the really clever part is that the system is designed so the aerodynamic forces during flight actually push the wingtip into the locked position.
Oh, that's smart. So the air itself is holding it closed rather than trying to pry it open.
Exactly. They are literally using the physics of flight as a fail-safe.
That is brilliant. And, that intense focus on aerodynamic efficiency brings us to the actual performance numbers Boeing is claiming here.
Right, the efficiency jump.
Because the entire justification for those massive wings and the GE9X engines is to drive down costs while supposedly improving the passenger experience.
And the numbers they are projecting are incredibly aggressive for an industry as mature as commercial aviation.
I mean, looking at the specs, Boeing states the 777-9 will achieve 20% lower fuel use and emissions compared to the airplanes it replaces.
Which is huge.
And a 10% lower overall operating cost than the competition. But, okay, the number I really want to interrogate here is the noise.
Ah, yes. The 40% smaller noise footprint.
Right, because if you're listening to this and you live a mile from a runway, you are probably rolling your eyes right now. Like a 40% smaller noise footprint sounds amazing on a glossy brochure.
It does.
But is that an actual physical difference you and I will hear when we're trying to sleep? Or is it just corporate math designed for an environmental report?
No, it's a completely valid skepticism. But to understand that metric, we actually have to look at how modern jet engines generate thrust and noise.
Okay, break that down for us.
So the G9X is a high-bypass turbofan. Now, in older, much louder jet engines, most of the air went directly into the jet core, mixed with fuel, ignited, and blasted out the back at supersonic speeds.
Just a raw explosion.
Pretty much. And that violent shearing between the incredibly fast hot exhaust and the static cold air outside, that is what causes that deafening, ripping roar during takeoff.
So how does adding a massive engine on the 777X fix that? I mean, wouldn't a bigger engine just mean louder noise?
Counterintuitively, no. In a high bypass engine, you have those massive fan blades at the front, right?
Yeah, the ones that look like a giant spiral.
Exactly. They pull in a huge volume of air, but the vast majority of that air actually bypasses the fiery core entirely.
Wait, it doesn't go into the engine core?
Nope. It flows around the outside of the core, and that creates this thick cushion of slower, cooler air that wraps completely around the high-speed exhaust coming out of the back.
Oh, wow. So the engine is essentially muffling itself with a blanket of cold air.
That's exactly it. Because the engine is so large, it generates massive thrust by moving a very large volume of air relatively slowly, instead of moving a tiny amount of air violently fast.
And that reduces the shearing effect?
Right. Combine that with those high-lift folding rings, and the plane can climb to a higher altitude much faster after takeoff. And in acoustics, distance is your absolute best silencer.
Okay, so a 40% footprint reduction means the geographical circle on the ground that actually gets blasted with heavy noise literally shrinks.
Exactly. You might find your house is now outside the blast zone when a 777X takes off, whereas an older jet would have rattled your windows.
That is legitimately impressive. And it seems like that engineering mindset applies to the inside of the cabin, too. The sources mention the cabin architecture draws heavily from the 787 Dreamliner innovations.
Yes, the passenger experience upgrades.
And I know from personal experience that the Dreamliner just feels different. Like if you've ever flown long haul and felt that dry throat exhaustion, that pounding headache, the Dreamliner somehow lessens that. How is the 777X borrowing that tech?
Well, it all comes down to the materials used to build the fuselage. See, older planes are made primarily of aluminum.
Right.
And aluminum is highly susceptible to metal fatigue and corrosion from moisture.
Oh, so it rusts.
Basically, yeah. So to prevent the plane from rusting from the inside out, airlines are forced to pump bone-dry air into the cabin.
Which explains why you feel like a raisin after a 12-hour flight.
Exactly. And because aluminum expands and contracts with pressure, they can't pressurize the cabin too heavily without stressing the metal. So flying on an older jet is essentially like spending 12 hours in a very dry desert at 8,000 feet of altitude.
That sounds miserable when you put it like that.
It is, but by using advanced composite materials, carbon fiber reinforced polymers, the fuselage doesn't corrode from moisture the way aluminum does.
Oh, so they can pump the humidity back in.
Exactly. And the carbon fiber is physically stronger against internal pressure. So on the 777X, they can pressurize the cabin to feel like you're only at 6,000 feet of altitude instead of 8,000.
That fundamentally changes the physiological toll the flight takes on your body.
It really does. It's a much more comfortable environment.
Okay, so to recap the efficiency side, we have an aircraft that burns 20% less fuel, doesn't wake up the neighbors, and leaves passengers way less dehydrated.
Pretty compelling pitch.
It is. But, a 20% fuel savings isn't a magic bullet if the plane itself is the wrong size for an airline's actual route.
Oh, absolutely not.
Because an airline flying short, packed hops between hubs like Chicago and Atlanta, they have completely different physics and economics to deal with than an airline flying 16 hours straight from Doha to LA.
And this is where we see Boeing shifting from purely aeronautical engineering into portfolio management, because you simply can't solve global logistics with a single airframe.
Right. And looking at the source data, Boeing is offering 3 distinct variants built on this same 777X foundation.
The family dynamic.
Yeah. So we've been talking mostly about the 777-9. That model carries 426 passengers with a range of 7,285 nautical miles.
Which is about 13,500 kilometers.
All right. But then there's the 777-. It's physically a shorter plane, dropping passenger capacity down to 395, but it pushes the range out to an astonishing 8,745 nautical miles.
Over 16,000 kilometers.
It's crazy. And finally, there's the 777-8 freighter, built for pure cargo, boasting a gross structural payload of 118 tons.
And a range of 4,410 nautical miles. The relationship between the 777-9 and the 777-8 is a classic illustration of the payload range curve in aviation.
Okay, break that down for me. What exactly is the payload range curve?
So an aircraft has a strict maximum takeoff weight. You only have so much weight you can allocate between passengers, cargo, and fuel.
It's a zero-sum game.
Exactly. Now, the 777-9 is optimized for density. It maximizes payload by putting 426 seats in the cabin to capture as much ticket revenue as possible on popular trunk routes.
Okay.
But carrying all those people and their heavy luggage means you simply can't fill every single crevice of the fuel tanks without exceeding the absolute weight limits.
Ah, I see. So to fly further, you literally have to kick people off
Yep.
the plane.
That's the physics of it. The 777-8 essentially trades fuselage length and passenger weight for fuel volume. By shrinking the plane and removing about 30 seats, they free up the weight allowance to carry thousands of extra gallons of jet fuel.
And that's how you unlock those ultra-long-haul routes, like flying nonstop across the Pacific. It's like a lineup of cars, really. The 777-9 is your high-capacity people mover for popular routes. The 777-8 is the ultra-long-range road tripper.
And the freighter's the heavy-duty pickup truck.
Exactly. 118 tons of cargo. Just to put that in perspective for you listening, 118 tons is roughly the weight of 60 standard passenger cars.
It's massive.
The structural reinforcements to the floorboards and the center of gravity calculations for that kind of dead weight must be absolutely insane.
They really are. But the genius here, and what Boeing heavily highlights in the sources as seamless integration, is that all 3 of these incredibly different missions are flown by planes with the exact same core architecture.
Which brings up a phrase Boeing keeps repeating in these materials: low risk, profitable growth.
Right.
And I'm looking at this claim, and honestly, to me, low risk in massive corporate operations usually just means don't change anything.
It often does, yeah.
So how do you introduce a brand new folding wing aircraft into a fleet and look an airline CEO in the eye and call it low risk?
Well, because the highest risk for an airline isn't actually the physical airplane, it's the entire ecosystem required to support it.
What do you mean?
Let's say a major corporation decides overnight to switch all of their thousands of computers from Windows to Mac.
Okay.
The cost isn't just buying the new laptops. The real cost is the downtime. It's retraining every single employee who suddenly doesn't know the keyboard shortcuts.
Right, the learning curve.
It's replacing all the proprietary software. It's retraining the entire IT department to troubleshoot a completely alien architecture.
The friction is astronomical.
Exactly. And in aviation, that kind of friction is deadly to profit margins. If you buy an aircraft from a completely different manufacturer or even a totally new clean sheet design, your pilots need weeks in expensive simulators to earn a new type rating.
Just to be legally allowed to fly it.
Right. Your mechanics need to learn entirely new maintenance protocols. You have to lease warehouses just to store a completely different inventory of spare parts.
Ah, I see the strategy now. By keeping the cockpit layout, the software logic, and the core systems deeply related to the older 777s and the 787 Dreamliners, the friction just disappears.
Exactly. A pilot who already flies a 777 or a 787 can transition to the 777X with very minimal retraining.
And the mechanics look at the landing gear and already understand the basic mechanical philosophy.
Boeing isn't just selling an airplane here, they are selling a plug-and-play upgrade for the airline's existing infrastructure.
But, no matter how perfectly the software integrates or how cleverly the wings fold on a computer, a CAD drawing doesn't fly.
No, it does not.
Putting a machine with an untested mechanical hinge and a 118-ton payload capacity into the sky over populated areas requires a staggering level of proof.
Because aviation history is littered with brilliant blueprints that failed violently when exposed to reality.
Which really explains the massive testing regimen detailed in our sources. Because Boeing didn't just provide specs, they provided a whole catalog of video evidence showing this plane being completely abused.
They are heavily publicizing the stress testing.
Yeah, I mean, the titles of these internal testing videos read more like a catalog for extreme sports than a corporate audit.
They really do.
We have things like crosswind testing, where they intentionally try to land the plane sideways in severe weather. We've got 7779 Curacao landing, non-destructive inspection, and 777 brakes testing.
And they even highlight Q&A sessions with Ted Grady, the chief pilot for the 777X program.
Right. But my question is, why make this such a public spectacle? Most corporate R&D, especially in aerospace and defense, is kept behind tightly locked doors.
True. But aerospace is uniquely dependent on psychological engineering alongside the mechanical engineering.
The philological engineering.
Yeah. I mean, look at the overarching corporate structure surrounding this plane and the source materials. You have Phantom Works, which develops highly classified tech.
Yeah.
You have the Cascade Climate Impact Model and Global Services. But the division they are deliberately leading with is the Safety and Quality Plan, overseen by a Chief Aerospace Safety Officer.
Because they explicitly state in the source, and I quote, "Our work begins and ends with safety. It's ingrained in everything we do." Which, sounds great on a slide, but talk is cheap.
Exactly. Talk is cheap. When you introduce novel technology, especially heavy moving parts on a wing, you are battling the inherent human fear of the unknown.
Right.
An airline won't buy it, regulators won't certify it, and passengers definitely won't fly on it if there is even a shadow of doubt. So you don't just tell them the brakes work, you show them a maximum energy rejected takeoff test.
Okay, what does that test actually look like?
It is intense. You load the plane to its absolute maximum weight. You accelerate it down the runway to the exact speed of liftoff, and then you slam on the brakes without using any reverse thrust from the engines.
Just raw brake power.
Yes. The carbon brake discs have to absorb tens of millions of foot-pounds of kinetic energy, converting it instantly into heat. The brakes literally glow bright orange and catch fire. And the test requires the plane to sit there on the tarmac for 5 minutes while the fire burns, proving the heat won't spread to the tires or the fuselage before emergency crews can arrive.
That is utterly terrifying, but incredibly reassuring to know they push it that far.
It is. And seeing Chief Pilot Ted Grady calmly walking through these extreme scenarios on video, it's highly calculated to project total control.
It's transparency as a strategic weapon.
Exactly. You're proving to the regulators that your math is sound. You're proving to the public that the cabin is safe. And crucially, you are signaling to the financial markets that the program is stable and de-risked.
And the markets clearly pay attention to that kind of transparency. The source material actually includes a snapshot of Boeing's stock price.
Yeah, the real-time financial impact.
We've got the ticker symbol BA on the New York Stock Exchange sitting at 223.76, up 4.6 on today's date, April 22, 2026.
Because Wall Street doesn't just invest in cool airplanes, they invest in predictable, profitable ecosystems.
Right.
When investors look at the 777X, they see an aircraft that solves the aerodynamic problem of fuel burn without requiring airports to pour billions into new concrete.
They see a family of variants that cover every profitable route an airline could possibly want,
while seamlessly integrating into existing fleets to keep training and maintenance costs near zero.
It's really the ultimate synthesis of physics and economics.
It is. And when a company demonstrates that they can execute that synthesis safely and proves it through brutal, transparent testing well, that confidence translates directly into that 223.76 valuation.
So wrapping this all up, when we started looking at this stack of documents, the folding wing kind of seemed like a futuristic gimmick, didn't it?
It really did.
But peeling back the layers, it's clear that it is the literal linchpin of a massive global strategy. By physically folding a 71.8-meter wing down to 64.9 meters, this aircraft adapts to the airports we already have.
While using the aerodynamic superiority of that extended span to slash fuel consumption by 20%.
Right, and using those high bypass engines to shrink the noise footprint by 40%.
Add in a composite fuselage that reduces passenger fatigue, and a family of variants capable of moving either 426 people across an ocean or hauling 118 tons of heavy freight.
Wait, no ellipses, hauling 118 tons of heavy freight.
Yeah.
And you have an aircraft designed to dominate the next era of commercial flight.
Without requiring a complete rewrite of the airline's operating manual, it operates precisely at the intersection of extreme engineering and practical reality.
It really does. But, going through all this, it leaves you with one really profound image to chew on.
What's that?
Well, we have reached a point in aviation where the laws of aerodynamics and the demands for efficiency have completely outpaced the physical footprint of our cities.
Oh, wow. Yeah.
The 777X literally has to fold itself to fit into the world we've built. And as you demand even greener, faster, and more efficient travel in the decades to come, it really makes you wonder.
It's hitting a wall.
Exactly. Are we approaching the moment where the next great leap in human flight won't be constrained by the power of our jet engines or, the ingenuity of our engineers, but simply by the rigid concrete of our airport gates?
That's a fascinating way to look at it.
Definitely something to think about the next time you're sitting on the tarmac looking out the window and watching that giant metal wing lock into place.